Hello, my name is Jamie Tayar, and I'd like to talk to you today about my recent paper entitled The Correlation Between Mixing Length and Metallicity on the Giant Branch, Implications for Ages in the Gaia Era. In this paper, we're using the over 3,000 first ascent red giants of the Apocask sample to test the stellar models of evolved low-mass stars. These are stars where we have astroseismology from the Kepler satellite, which gives us their mass, radius, surface gravity, and evolutionary state. They also have spectroscopy from the Apogee survey, which gives us their temperature, metallicity, and alpha element enhancement. Since we know so much about these stars, we can predict the exact temperature they should have at the measured gravity. We show here the temperatures and gravities of the stars in our sample around 1.2 solar masses, color-coded by metallicity. You can immediately see that the points don't line up with the model predictions. In red, the metal-rich stars are too hot compared to the metal-rich models, whereas the opposite is true for metal-poor stars in blue. We quantify this by measuring a temperature offset for each star from a model of the appropriate mass, metallicity, and composition at the measured gravity. When we do this for all the stars in our sample and bin the data, we find that the predicted temperatures of our models are off in a metallicity-dependent way with a slope of almost 100 Kelvin per dex. We are confident that this is not just a problem with our models, since we see a similar trend if we use the parsec grid of models, although the normalization is different. We also check that the offset we're finding is not due to our assumptions about the atmosphere boundary condition, helium enrichment, or astroseismic mass scale. We then look at the implications this temperature offset would have on ages inferred using the recently released Gaia data. Using a precise luminosity from Gaia and a temperature and metallicity measurement, one could use a solar calibrated model to infer the mass of a red giant, and therefore its age. Unfortunately, if the model's in the wrong place, you would infer the wrong mass of the star, and therefore the wrong age, with metallicity-dependent age errors that can be as large as several gigayears. We suspect the offset in temperatures of the models is due to our assumption that all stars have the same convective efficiency as the Sun. Three-dimensional simulations of convection predict this convective mixing length should vary as a function of temperature, metallicity, and gravity. And so we fit for each star in our sample the mixing length we would have predicted from the three-dimensional models. We also calculate for each star in our sample the effective mixing length we would need to make the model temperatures agree with the observations. This produces a metallicity-dependent effective mixing length, which is interestingly discrepant from the predictions of the three-dimensional models, something that is worthy of further investigation. If you're interested in the details of our analysis or the additional implications of our results, check out our recent paper, which was posted on the archive today.